Welcome to the second day of the two-day international webinar on Futuristic Trends in Mathematics 2021, organized by the Department of Pure and Science Mathematics, Midnapore City College. Yesterday, we had an amazing first half with Professor Sankar Kumar Roy, Professor Alexander Vasin, and Dr. Mohammad Akbari Tootkaboni. Today, we will strive for more with Professor Shyamal Kumar Mondal, Dr. Lorenzo Luperi, Baglini, and Dr. Sadia Samar Ali. Now, I would like to request Dr. Shyamal Kumar Das to say something to start the webinar.
Good afternoon, everyone. Welcome to the second day of our two-day international webinar on Futuristic Trends in Mathematics 2021, organized by the Department of Pure and Applied Science, Mathematics, Midnapore City College. We already had a wonderful first day. Today will be enriching again for us, as we have Professor Shyamal Kumar Mondal, Dr. Lorenzo Luperi Baglini, and Dr. Sadia Samar Ali with us today. This webinar is not only fulfilling academic purpose, but also it has brought different nations and cultures together. This harmony is important amidst this global pandemic. Hopes is what we can really on. I eagerly perceive that this webinar will serve its purpose fully till the end. I am very glad that we have managed to organize such a international webinar of global proportion. It is a huge opportunity for all of us. Without further delay, I am concluding my speech, wishing a very successful second half. Thank you all.
Thanks, Dr. Das. Now it is time to start the webinar sessions of our second day. First, I would like to request Professor Sankar Kumar Roy to chair the session of Professor Shyamal Kumar Mondal. Sir, to you.
Hello, am I audible to all of you? Hello?
Yes.
Yes, audible.
Yes, sir.
Good afternoon to everyone. This is the second day of today's international webinar organized by Midnapore City College. Today, first speaker is Professor Shyamal Kumar Mondal. Before starting his lecture, I am to give a small introduction about him. Professor Shyamal Kumar Mondal completed his bachelor's and master's from Vidyasagar University, and thereafter he completed his PhD in mathematics from Vidyasagar University in 2004. Before that, he also completed his MTech in computer application from Indian Institute of Technology, former it was ISN, Dhanbad, Jharkhand, India. Now Professor Mondal is HOD of our Department of Applied Mathematics. Basically, Professor Mondal doing research in varieties of fields. As for example, he mainly involved in operations research, meteorology, fuzzy set theory, subset theory, and subcomputing, as well as the functional biomathematics. He has published more than 150 research papers in different reputed international journals in various publishers, Springer, etc. Till now, 14 students have been awarded under his guidance, and 4 students have submitted, and 6 students are pursuing PhD. He has delivered many lectures as an invited international level conference in India as well as the abroad, like Vietnam, Bangladesh, etc. He has completed 3 CSR UGC projects as a principal investigator in operation research, especially in inventory production problem in type 2 fuzzy environment. And Professor Mondal is very good teacher. He is very successful teacher also. the students like him for attending his class. With which start his interesting lecture in front of many young researchers and the students of Midnapore City College as well as the other institutes. I request to Professor Mondal, please start your session now.
Good morning, everyone. Thank you, Chairperson Professor Sankar Kumar Roy, for introducing me in this webinar. First of all, I convey my deepest congratulations, thanks Director of this institute, Dr. Pradeep Ghosh, and Principal, Dr. Sudipto Chakraborty, and departmental teachers, Shyamal, Abdul-Aziz, also I think Abhishek also teachers, and other faculty also. And I also wishes all my beloved participants in this webinar. Actually, I have very small knowledge, but from this knowledge, I want to share with you whatever I know. In this aspect, I want to give brief discussions about new area of optimization. So for this purpose, I am showing our presentation slide. You see and enjoy the presentations. I think it is visible. You are seeing the first page of my presentations. Application of
Professor Mondal, till now it is not visible.
Oh, not visible.
Yeah.
We have to presentation more. Okay. Okay. I think now it is visible. It is visible.
Yes, it is visible now.
Okay. So, my discussion about application of natural events in optimization. Optimization is a very known field to our students in mathematics. We know how to optimize a function that is actually taught in HS level and graduation level, also in MSc level. But here you are seeing that title is application of natural events. So many natural events are in our nature, in our surrounding us. And using that knowledge, how to optimize a function, that can be discussed here very briefly. What are you seeing in this space? You are seeing two pictures. In the sky, there is birds are flying. Beautiful sky, beautiful blue sky. And in the sky, so many birds together, and in discipline, they are flying. Why? In search of food, basically. Another picture you are seeing, there is a pond or river or sea. There is swimming a flock of fishes. They also swimming together also. Actually, this picture teaches us how to apply their knowledge in our daily optimization technique. Both pictures, both fish and birds, they actually search their foods in Delhi. For this purpose, they are flying the sky or they are swimming in the pond. But purpose is to search a food. How it is possible to get a food in short time, in short place? For this purpose, they are actually doing such work together. So, using this concept, using this phenomena, using this natural event, how we are using this method in optimization, that is described very briefly also. Just actually our motivation is to inspire you to study about this matter, which is non-classical techniques actually for optimization. So optimization we have to use. So what is optimization? You know, everyone know what is optimization. Optimization, that is a procedure, which procedure actually help us to find one or more feasible solutions. Feasible solutions means the solutions which satisfy all restriction, all criteria which are imposed by us. And that solutions correspond to extreme value. Extreme value means that is optimum. Either that is best value with respect to objective functions. Obviously, in each problem, there is some objective, one objective or multiple objective. So, to satisfy that objective, we have to find out some point, some decision, some solutions. Which solutions give the best value of the objective function? That is actually optimization procedure. So for this purpose, in classical method, that is differential calculus, you know, we have to differentiate the objective functions. Here we are showing a graphical representation of a function you are seeing, and you know on these functions at which place there is optimum value. You are seeing that there are many points at which optimum value exists. Among them, one is global optimum. To get this value mathematically, that means using calculus, we have to take differentiation. Certain procedure is there. Maintaining that procedure, we are able to get that point at which the function is that means optimum. So this is actually optimization. How these optimum solutions are obtained, that is what is the essence. What is the essence of optimization algorithm? Now basically, in which place where directly it is not possible to derivative the objective functions, but otherwise objective function, the solution gets derivative. When we are getting the derivative, that is laborious. That is not easy to get the derivative part. In that case, basically we use numerically to get the optimum solution. So main motto is starting from a initial point which is used. That is, here you see x1 is the initial point. From x1, we then want to get another point x2 in such a way that that point gives better solution, better performance with respect to x1. In this way, we proceed. So you see, x at generation t plus 1, the function of the decision variable is x, and that can be obtained using the value just previous iteration, that is xt. So there are so many parameters may exist. For example, here is alpha. This is basically essence. So that is okay. So we have some methods in calculus. Why it is needed? Another non-traditional method, non-classical method. Obviously, there is some difficulties in calculus-based methods. Here we are seeing some difficulties in calculus-based method. You see, first of all, first one is convergence to an optimal solution. Depends on the chosen initial solution. Basically, more cases, depending on the initial point from which we started our iteration, depending that convergence depends. Actually, we are not able to get the exact optimum solutions. Before that, that point is converged. So convergence to an optimal solution depends on the chosen initial solution. That is one problem. Another problem is most algorithms to get stuck to suboptimal solution, not exact solutions. Another is this algorithm is efficient in solving one search and optimization problem that may not be efficient in solving different problems. That is classical methods by which we get the optimal solutions. One method is very good in one problem, but that method is not good in another problem. That is algorithm actually here depends from problem to problem. That is the problem. So by a single algorithm, we are not able to get the optimum solutions in every optimization problem. That is another problem in calculus-based method. And other is such types of algorithms are not efficient in handling discrete variables. We know calculus methods actually applied only when function is continuous. Otherwise, the calculus method cannot be applied. So if in a problem there is some discrete decision variables, in that problem we cannot apply a calculus-based method. So these types of drawbacks are there in calculus-based method. To overcome these methods, at different times, different researchers developed different non-traditional methods. Non-traditional method by which we can get the optimizations. Among them, one is particle swarm optimization. You see, PSO, particle swarm optimizations. Basically, this optimization technique is developed in 1995 by Eberhard and Kennedy. And this algorithm, that is PSO algorithm, basically simulates the social behavior, animal social behavior. using animal social behavior, that method is applied in optimization. Social behavior of animals including insect, herbs, birds, fishes. So these types of animals, insect, birds, fishes, basically they swarms conform a cooperative way to find food, and each member of this group, of this swarm, you see in the picture, there is so many members are there, so many birds, so many fishes in a group is there. So main way is to find a food, and each member in the swarms keeps changing the search patterns according to the learning experience of its own and others members. They actually scan every places, and from each place they learn in which place there is possible to exist a food. Individually they learn and collectively they learn. And this technique are using here to optimize a function mathematically. For this purpose, there is actually algorithm is there. Just I want to give some notion. Here you see basically each particle has velocity. Suppose here vi velocity, ith particle velocity vi at generation t, by at time t, and at that time position vector, that is position is xi at t time of ith particle, and whole populations, the whole group, whole swarm, whole population has a current based solutions, and each have historical based solutions. Using this, actually we update the velocity. What will be the next velocity? That means from current position of each member, each fish, each bird, each ant, they move in which direction? In which direction there is possibility to get the food. So each time, each step, we have to update the velocity, and with that we change the positions. So first of all, we update here velocity at time t. This is velocity, and after subsequent time, that is t plus 1, what will be velocity? This one will be velocity, and then this velocity is added with the position, so we get the next positions. This is very simple mode actually. There, it is not just so much easy. Just we are seeing here, but notion is this. And here there is so many parameters. That is the learning parameters. There are also some random numbers. You are seeing the random numbers. That is actually, this method is a stochastic method actually. Another thing is simulated annealing. You are seeing simulated annealing. This is actually another matter. When actually some metals are melted, heated, some metals are heated, then that metals are cooled gradually. Why? To get a crystalline form. To get a crystalline form. You are seeing here melted metal is pouring, and gradually a temperature is decreased in such a way that metals form a crystalline. These techniques are used in optimizations. So this is the algorithm, a simple algorithm by which we are able to optimize the functions. So for this purpose, we have to choose the initial point, x0, termination criterion, epsilon, and set T, that is temperature actually, T sufficiently high. Number of iterations we have to perform, that is N, initially T0. So every time we have to calculate the neighboring point, that is xt plus 1 on xt. Normally it is taken as a random point from the neighborhood, and then we have to compare. We check the value at xt and xt plus 1. That is actually known as energy level, energy at xt point and xt plus 1 point. If that difference is less than 0, then we change the iteration t plus 1. Otherwise, we can do some operations in such a way that we get the better point. But noting the main principle, main basic rules, the temperature is gradually down to get the crystalline, that is energy is less. That techniques are used here in simulated annealing. So these two are natural events we are seeing in our surroundings, and from that we have the knowledge to optimize the objective functions. Another thing is genetic algorithm. It is another technique, genetic algorithm. Actually, this algorithm is discovered by John Holland, Professor John Holland, University of Michigan, in 1975. It was actually induced from his brain. Thereafter, this algorithm has developed tremendously. He and his students contributed much more, and till now there is going on research to update this methods, this algorithm, that is the genetic algorithms. What is the advantage actually, genetic algorithm? Now, genetic algorithm advantage basically is that here it is not required for derivative information. In this case, there is not required or derivative information. That is the main advantage. No derivative, no calculus. No derivative, no calculus. And it is faster and more efficient than compared to traditional methods. And it has very good parallel capabilities actually. And it optimizes the function which are continuous and discrete, both. Also, this algorithm can be applied in multi-objective optimization also. Not a single objective, multi-objective. And another is it provides a list of good solutions. Normally, when we apply classical methods to get the optimum value, we get only one point, one value, one solutions, not more than. Basically, there may be many optimum solutions exist, but it is not possible by classical methods. It is able to get by genetic algorithm. So there are a list of good solutions. And always we get a solution in this case. And it is very useful when search space is very large. When search space is very large, in that case, classical methods is very slow, basically. So many advantages there in genetic algorithms. For that, recently in computational field, basically in which optimization is required in that case, genetic algorithms are used by young researchers. What is the basic thing actually in genetic algorithms? That is the actual evolution. That is change of habit. So you are seeing a series of human beings from ancient times. Gradually, the structure of human beings shape has been changed. From beginning until now, the human being becoming smarter and smarter. So why? Because actually human being actually changes his characteristic in a critical situation, in bad environment. They overcome the bad environment, and for long times that can be affected in their gene structures. That means there is evoluted in genes. So it is the basic thing actually in genetic algorithm, that is the evolution, that is change of his characteristic when they facing the critical situations, bad situation, bad environment. This is one story you are seeing. Stories, you see that rabbits, at a given time, there is a population of rabbits. A population of rabbits, that is, some rabbits are there, and among them, some are smarter and faster than other rabbits. Obviously, there are also, in this place also, there is foxes in jungle, in that place, in that area, in that jungle. So, those rabbits which are faster and smarter, they are less likely to be eaten. They are less likely to be eaten by foxes because they are faster and smarter. When fox catches, they run very quickly, fastly. And more of them, as a result, they survive. As a result, they survive. Of course, some of they are slower, dumber, and they also survive sometimes because they are lucky. So this surviving population of rabbits, when start their breeding, result a good mixture of rabbits genetic material. Some slow rabbits breed with faster rabbit, and some fast with faster, and some smart rabbit with dumb rabbits, so on, in this way. So basically thing is that the rabbits which are faster and smarter, they breeds, their possibility of breeding smart and faster rabbit. That is the thing, because we know when parents is educated, basically there is possible for education of their children. And this logic has been adopted in this algorithm actually. So in this algorithm, basic thing is chromosome. You know, chromosome is the main characteristic of the human and every animal, every organism in the world. And each chromosome, there is DNA, RNA, also gene. Many genes are there which carries the different characteristic which are expressed by us. That chromosome. So what is the basic terminology of this algorithm? basic terminology is populations, chromosome, gene, allele, etc. What is populations in this algorithm? It is basically a subset of all possible solutions to the given problem. Population for genetic algorithm, that is basically similar to the population of human beings, like that. And each member actually in these populations, that is the solution, the candidate solution. And that is actually chromosome. So chromosome here is known as solution. Each solution that is known as actually chromosome. And what is the gene? The gene is one element, position of the chromosome. You are seeing here a picture, you see, this is the one chromosome. This is one chromosome. And there is some number 01, 01, 11, etc. These are the main characteristics of the chromosome. That is, these are the gene. These are the gene which carries some characteristic. Because if you change 0 to 1, actual value will be changed. So these positions have some characteristics. This position bears some properties, some characteristic. That is biologically which is known as gene, which carries the characteristic of us. In this case, 0, 1, etc. So it is actually here called gene. And this position contains either 1 or 0 value in binary form. That is known as allele. So allele, that is the value which a gene takes in particular chromosomes. Another thing is genotype. What is the genotype? The genotype is the population in computation space. In the computation space, solutions are represented in a way which can be easily understood and manipulated using computing system. That is the genotype. Genotype also populations. Also phenotype also populations. But what is the difference between genotype and phenotype? The genotype is the population in the computation field. Actually, when we want to solve a problem, we have to define that problem mathematically. So representation is different. When we are going to solve, that is represented mathematically. There is mathematical model. Then that model, when we have to solve or get the solution from that, they have to transfer, they have to alter another form. So here also, phenotype basically the population in real world situation, the populations, but in which are seen in the real world population, that cannot be solved directly. So we have to require a transformation from this set to this set, that set. So genotype is that population in computational world. When we computing, in that case, that is that population is genotype, and phenotype is the real world populations. So obviously you are saying from phenotype to genotype or genotype to phenotype, there is required decoding and encoding. Decoding and encoding is required for simple problem. For simple problem, phenotype and genotype pairs are same. However, in most of the cases, phenotype and genotype pairs are different. Decoding is the process of transforming a solution from genotype to the phenotype base, while encoding is the process transforming from phenotype to genotype base. You are seeing here, this is phenotype base, that is actual solution base, and genotype base, that is computation base. In computation base, you are seeing a solution 0, 1, etc. But phenotype base, that will be actually X, Y, Z like this variable. So that is required encoding, phenotype to genotype, that is encoding, and genotype to phenotype, that decoding. So these are required. These are basic characteristic of genetic algorithm. And now we discuss the components of genetic algorithm. What are the components in genetic algorithm? When we developed an algorithm in genetic algorithm methods, there is some stage, parameters, procedure that is shown here. First of all, one component is parameter of genetic algorithm. Parameters of genetic algorithms. There are some parameters we will discuss later. And then presentation of chromosome. That means we have to represent, that is, we have to phenotype to, we have to convert phenotype to genotype. Some transforming rules. So there is some representation, how chromosome, that is solution, can be represented. Then initialization, there is another procedure, another step, that is the initialization. And then evaluation functions, then selection process. After that, genetic operators, that is crossover and mutation. Just like biologically, when is species generate offspring, in that case, this method is required. You know, you studied crossover mutations that is performed in chromosome, and with this method, by this method, actually some material of parents, that is father and mother, material has exchanged in their babies, that is offspring, that is sons and daughter, like this, and then termination criteria. These are the basic step, obviously. Basic classical genetic algorithm is this one. First of all, population size. What is the population size basically? That means how many chromosomes are required to get the optimum solution of a problem. That indicated by pop size. So you see, to initialize the population, we can simply set some pop size number of chromosomes randomly. Pop size number. It may be 10, 20, 50, hundreds, like this numbers. You take care about the solution procedure. Basically, in this method, that means non-traditional, that means genetic algorithm in this method, there is not a single point. Basically, in classical methods, when we solve the problem, that means when we optimize a problem, we start the procedure taking a one point, initial point, you know, Newton-Raphson method, iteration method, by which we get a solution of an equation. So in that case, we take only one point, and from that point, we can generate another point in this way. But in this technique, there is not a single point, there is many points. So many points is there. But how many points? That is some rules. As we say, you cannot take the number of members, number of chromosomes, that is pop size. Pop size may not be any number. Because of, if population size is too small, then genetic algorithm may converge too quickly. And if it is too large, then genetic algorithm may waste computational resource and waiting time. Obviously, if you take large number of points, for large number of points, you require a huge pace, and it takes also computational times. So that is the another matter. So take care about this. You have to set the population size in your problem. That is one thing. One meter, you have to take care about the population science. Next one is probability of crossover, another parameter. This is also another parameter. Probability of crossover. There is an operation of crossover, you know, when biologically we perform the crossover, there is required two members. And between two members, crossover is done. So, among how many members crossover can be performed? That is the important factor. That is actually known as probability of crossover. Normally, it is taken 0.8 to 0.95, but this is not hard and fast. And another thing is probability of mutations. This is also another parameter. How many mutations can be performed among the populations that can be obtained from this number. And last parameter, that is the maximum number of generations. Then so it is the iterative methods. By iteration, from one iteration to another iteration, solution is updated. So how many number of generations we perform the iteration, that is important factor. So in this case, the maximum number of generations are required to use this method. Next one is representation of chromosome. How chromosomes are represented. There are many methods for representations. Just here, four names you are seeing: binary representation, floating point representation, octal representation, hexadecimal representations. First of all, binary representation you see. Binary representation. That means how phenotype to genotype will be converted. What will be the representation? In this case, binary vector is considered. Binary vector, you are seeing the picture, that is the binary vector. You know binary number that consists of 0 and 1, the binary vector. The binary vector, that is sequence of binary number, sequence of 0, 1, that is taken as a chromosome. That is a chromosome. So, which are you seeing here in the page, that is one chromosome, and this chromosome basically represent some real value of the variable, So each chromosome is coded using same number of bits. Each chromosome. If there is 10, 20, 50 chromosome, so each chromosome have same number of bits. But length of vector, that means how many numbers, how many 0 and 1 will be there in the chromosome, that depends on the required precision. That means how precision you are required in your problem. Depending on that, length of the vectors are determined. So each chromosome is a vector of inwards which is equal to number of elements per chromosome, and precision of such approach depends on the number of bits actually, and that is actually UB, upper boundary minus lower boundary by 2 to the power minus 1. And like this, we are speaking. This is the binary representation. Ultimately, this is this representation we use 0 and 1. For example, just like one example has been given here. You see function f of x1, x2. Algebraic function you are seeing f1, x1, x2 equal to 21.5 plus x1 into sine 4 pi x1 plus x2 sine 20 pi x2. This is the objective functions. Actually, which have to optimized, and domain of variable x1 and x2 are this one. x1 belongs to minus 3 to 12.1, x2 4.1 to 5.8. So in this region, in these physical regions, you have to find out that point in which this function has maximum value or minimum value. That is the actual target in optimization. So for this purpose, when we are using the genetic algorithm, first of all, we have to represent the variable as a chromosome. For this purpose, here we have done some mathematics you are seeing actually. But I'm not discussing this one. But there is mechanism. If you want to try to understand, you can do that. That is very easy and very logical. How many bits are required? 18, 15. Just you see, this is the sequence 01 sequence. You see here 33 bits are there. 33 bits are there. But first 18 bits represent x1 and second 15 bits represent x2. Why 15 and 18? That depends on precision. That is taken here. And so you have to represent in this way, binary representation. This is the binary representation. This is the actually binary representation. Another representation is floating point representations. That means in this case, each chromosome vector is directly represented as a floating point number. Just you see here the pictures in which there is some number 0.5, 0.2, 0.3, etc. So this is one chromosome. This is one chromosome. That is here we directly use the floating. That means real number. That is real number. This is another representation. And this is some comparison with binary that is not discussed actually. Next step is initializations. So after making the representations, we have to initialize the set of member, that is population. So in this case, you see there are here in the here which are seeing here, there are 5 chromosomes are there. 5 chromosomes. V1, V2, V3, V4, V5. 5 chromosomes are seen here, and this is binary form. Obviously, this is a sequence of 01. This is the sequence of 01, but this sequence of 01 are generated randomly, basically, randomly. And when you convert this sequence in floating point representation, it will be in this form. It will be in this form: V1, V2, V3, V1, X1, X2, X1, X2, like this way. This is the floating point representations. And next step is evaluation functions. Evaluation functions. So after initializations, we have to get the objective functions value objective functions, and each point there is 5 points is there, either floating point representation or binary representation, and each point what is the objective value of the function. Suppose f of x is the objective function, which are given here from here. This is the objective function actually. So what are the objective functions value? What are the objective functions value? Just put it, you put in place of x1 and x2, and we get the value. You see here. At this point, for chromosome B1, the functional value is this one. Chromosome B2, functional value this one. Chromosome B3, functional value this one. For chromosome B4, this one and this one. So for 5 chromosomes, that is 5 solutions, there are 5 value of the objective functions. 5 objective functions, but different objective functions there. And but we are not granted among these there is optimum value or exist, that is granted. We have to target that value. How we reach there, that is the main things actually here. After that, after evolutions, we have to select. That is the mean. After evolutions, we have to select some members from these 5 members, among which crossover and mutation can be done. That means we have to get another set. We have to get another set of 5 points. Another set of 5 points. Using these 5 points, using these 5 chromosomes, we have to determine. We have to generate another 5 points. How? Just using crossover and mutation, 2 operations. Just like there is 2 human beings, father and mother, 2 persons there. From that 2 persons, we get 1 or more new offspring, new member. How? Just exchanging my crossover. I'm exchanging the materials among father and mother biologically. That is the main thing. Changing the gene value, gene positions, by which new offspring will be generated. Here also, this is 5. After using this, we get another. So this is required selection. That is very important thing. Selection. Using selection, there is different techniques. Raoulట్ selection, Futuristic universal sampling selection, tournament selection is there. Any one of these selections you can use, by which we can select on which member we can apply crossover and mutation. So for this is the yes. So this is that methods, these stochastic universal sampling methods. That is not required, tournament selection method. And then genetic operators, crossover and mutation. There are different types of crossover there. Single point, double point, multiple point, single point crossover, double point crossover, universal crossover, real world crossover, simple, arithmetic, heuristic, different things, but it is not so easy just from one lecture, one presentation, but is there. There is some technique, there is some methods. By using, we can do this one. And that is the termination. That is actually the flow of algorithm. That is populations, first of all populations, then evaluation, fitness, reproduction, crossover, mutation, then again populations. This is the basic. This is another flowchart, working principle. Okay, thank you.
Okay, thank you, Professor Mondal, for your nice lecture, how to optimize a function with the help of biological concept, or you can say a nature-inspired algorithm. I hope the participants, those are in this Google platform, they already enriched by listening to this lecture of Professor Mondal. If you have any question, you can send email to Professor Mondal individually also. Actually, we are moving short of time. With this few words, I must thank Professor Mondal for your valuable lecture. That will be helpful to move a long journey to the young researchers. Thank you very much.
Thank you, Professor Sankar Kumar Roy and the organizer. Thank you.
Thanks, sir, for your innovative ideas and presentation. Now it is time for the session of Dr. Lorenzo Luperi Baglini from Italy. I would like to request Professor Sankar Kumar Roy to chair it. Sir.
Thank you to the organizer for giving me the opportunity to session the chair. First of all, a very good afternoon from India to Italy, Professor Lorenzo Luperi. We are from the assistant professor, University of Milan.
Okay, thank
Department
you
of
very much.
Mathematics, Italy. Before starting your lecture, I want to give a short introduction about you, Professor Baglini. You have now holding a good position as Italian habilitations for associate professor in mathematical logic in 2008. And you have a lot of success throughout your career. You have in 2009 you are now the researcher position in mathematical logic, Department of Mathematics, University of Milan, and you also hold a post-senior postdoc position in F stand-alone project with non-standard methods for arm-set theory. You have a lot of things in which I want to mention about your research interest. Basically, Professor Baglini has interest on research in mathematical logic and its application, combinatorial number theory through non-standard analysis and ultra filters methods, application of non-standard analysis to analysis, Ramsey theory and mathematical physics, and your interest on nonlinear theories of generalized function and their application to analysis and mathematical physics, especially in the context of non-standard analysis, and so many things. We have many personal research grants from 2012, and as well as the other research grant also. Until now, we are teaching in University of Milan. I hope your enlightened lecture will enrich our young participants as the students and the researchers of Midnapore City College. I request to Professor Baglini, please start your innovative lecture to enrich the participants in this platform.
Okay, thank you very much for the kind invitation, and thanks to all the organizers for inviting me here, especially to Professor Patra. I will try to share the slides. Okay, I'm not really an expert in Google Meet. Here it is. So now you should be able to see the slide of the lecture. So please interrupt me for questions whenever you want. I will talk about non-standard methods in the partition regulator of equations. The talk is kind of divided in three parts. In the first part, I just want to give a bit of an historical perspective on what's the problem I'm gonna talk about, presenting the main results that we have in the literature in the past century, and focusing particularly on the most recent results. In the second part, I want to discuss a little bit about the methods that I'm using to study the problems in the area, which are based on ultrafilters and non-standard analysis. I don't assume that you know what ultrafilters and non-standard analysis are. And in the last part of the lecture, I will discuss some open problems in the area. So, combinatorial number theory is an area that has seen a lot of new results in the past few years. Combinatorial number theory lies in the intersection of combinatorics, so Ramsey theory, so result that talks about the existence of certain structure in, for example, the natural numbers, and number theory that talks about problems regarding the numbers, their densities, and so on. What's interesting in this area is that methods and results come from different several fields. So they have been proved using algebraic methods based on filters, ergodic theory, which is a rather different approach, discrete topological dynamics, analytic number theory, and so on. So you really have a lot of different ways to approach problems in this area. And I'm just presenting some of the ways. There are actually many more. More recently, and this will be what I will focus in the second part of the talk, several methods based on standard analysis have been developed. In particular, in two areas of combinatorial number theory. Ramsey result, so result talking about partitions of sets and which kind of structure can be found there, and density result that says that whenever you have a set with a lot of points, some structure has to arise. I will focus in this talk more on Ramsey result for time reasons, but there is a lot of research also going on for density results. Now, what are the problems about for someone that has never heard about combinatorial number theory? Arguably, the first result in the area is Schur theorem. Actually, Schur theorem was proven even before Ramsey theorem, because Schur theorem is from 1916, and if I remember correctly, Ramsey theorem is from 1924, something like that. Schur theorem was actually a lemma. It was interested in proving certain conditions for Fermat-like equations on finite fields. Actually, it was interested in proving that this Fermat-like equation can be solved, and it proved the following. If you take the natural numbers and you split the natural numbers in a finite amount of pieces, in one of the pieces, at least one of the pieces, you will find a Schur triple, meaning you will find A, B, and their sum. So basically, Schur theorem is saying that you cannot destroy sums just by finite partitioning the natural numbers. Do it as you wish, at least in one piece, you will have a sum. Schur theorem was generalized 10 years later by Bartel van der Velde, who actually proved that much more holds. If you split it, all the result will talk about splitting the natural numbers. So if you split the natural numbers in a finite amount of pieces, in at least one of the pieces, you will find arbitrarily long monochromatic arithmetic progressions, which means objects of the form. You will have x, x plus y, x plus 2y, and so on, all of the same color. For finite k, arbitrarily large but finite k. One question for you is, what if I ask about long arithmetic progression? Infinitely long arithmetic progression. Do I still have the result? Think about it. Now, in this form, it's not really true that this is a generalization of Schur. I wanted to present this form because it's the original one, but actually you can strengthen van der Velde theorem to ask that also y is in the same piece of the partition as x and x plus y and so on. And in this way, you see that the first three terms are Schur, and then you can ask much more. Now, probably the major result in the area was proven actually by Richard Rado around the time of van der Velde, shortly after van der Velde theorem. Richard Rado was able to characterize the partition regularity in an equation. Let me now fix precisely what's partition regularity of an equation. If you have a polynomial with integer coefficients, here I will focus with integer coefficients and not the natural numbers. Of course, things could be done much more in generality, but I don't think it's worth to do it here for this presentation. Now, we say that the equation polynomial equal to 0 is partition regular if and only if, whenever you split the natural numbers in finite amount of pieces, in one of the pieces you will find a solution of the equation. Schur theorem is just saying that the equation x plus y minus z equal to 0 is partition regular. And now Rado was able to completely characterize which linear equations are partition regular. Actually was able to characterize completely which systems of linear equations are partition regular, but here I want to focus only on single equation because the characterization is nicer. A linear equation of this form is partition regular if and only if the following condition, which is called Rado condition and will appear over and over and over again during this talk, is satisfied. The condition is there is a non-empty set of the coefficients that sums to 0. If you have Rado theorem, Schur is trivial to prove, because in Schur theorem, the equation that you have is x plus y minus z is equal to 0. The coefficients are 1, 1, and minus 1. And pick a positive 1 plus minus 1, the sum is 0. But this holds for any possible linear equation. And I also want to mention that this is one of my favorite theorems in mathematics, not just because I work in this area, but because if you check the definition of partition regularity of an equation, this is an extremely difficult definition to check, because you have to take the equation. In principle, you would have to consider all possible partitions of the natural numbers, and you have an uncountable quantity of this partition, and some of them have no structure at all. You have random partition, and you still have to prove that the given equation admits monochromatic solutions in any of these partitions. Rado theorem shows that this is actually equivalent to an easily computable condition. The easily computable condition is you have to find a non-empty set of coefficients that's up to 0. This can be computed. Now, in 1926, Zemeredi, Van der Velde proved his theorem about the partition regularity of arithmetic progression, which in 1936, there was a question by Ernst and Turan about a density version of this result. Meaning, Van der Velde tells that whenever you split the natural numbers in a sorry? Are there questions? I think there is some microphone that is open now, but I'm not sure if it's a question for me or not. I don't think it's a question.
Just a minute, Professor Baglini, please wait. Please, organizer, hello. Please unmute, mute the microphone, please. Okay, please carry on. Professor, please carry on.
Okay, so as I said, in 1926, Van der Velde proved the partition regularity of arithmetic progressions. You split the natural numbers in a finite amount of pieces. In one of the pieces, you will find an arbitrarily long arithmetic progression. The question is, do I have some kind of control on which set can I take and it will contain arbitrarily long arithmetic progression? And the question of Erdős and Turan was, for example, if I know that the set has high density, so it has a lot of points, does it automatically have to contain arbitrarily long arithmetic progressions? This question remained open for more than 30 years, and it was solved by Andre Zemeredi in the 70s. Zemeredi proved that if a set has a so-called positive upper density, it contains a lot of points, then it automatically has to contain structure. The structure being containing arbitrarily long arithmetic progression. This goes in the direction of the density result that I don't want to talk a lot about, but I wanted to mention this result for two reasons. The first is that Zemeredi got a Nobel Prize for solving this problem. So you get that the idea that this looks nicely framed as a problem, but it's extremely difficult. And the second is that exactly as the proof was extremely difficult, shortly after, Furstenberg started to see if a simplified proof could be found. And his idea was to use ergodic theory. I actually managed to find it's not a simple proof, but a simpler proof than the original one by Zemeredi by using ergodic theory. And this originated the use of ergodic theory in the area, which has been actually one of the two extremely prolific methods here. The other being ultrafilters. There are several different ones, but these two are really the two main tools in the area. And for example, using this method in 78, Sarkozy and Furstenberg proved that if a set has enough points, automatically it has to contain two numbers whose difference is a square. The other reason why this result is important is that all the results I presented so far are involved with linear equations. Rado talks about linear equations. When you work with linear equations, the nice thing that you have is that you're actually working with just one operation, because the only operation that is involved basically is the sum. When there is only one operation involved, there is a lot of different methods that you can use to study the problem. When you go to nonlinear problems, so nonlinear equations like x squared plus y squared equals z, there the situation is really different, because now you have two operations. You have products and you have sum, and mixing them is extremely complicated. And in fact, there are not a lot of nonlinear results, and most of them have been obtained really in the past few years. So first I want to present two trivial nonlinear results. The first is the multiplicative version of Rado theorem that tells us that a nonlinear Diophantine equation of the form product of variables to exponent equal to 1 is partition regular if and only if Rado for the exponents. But this is really an exercise because you can deduce this result just by the linear version of Rado using a transformation between Rado. Another trivial result is Lefman theorem, which is actually Rado where every variable is not with an exponent 1, but with a fractional exponent, but the fraction is always the same. So equation like square root of x plus square root of y equals square root of z. And actually, here again, Rado condition. The partition regularity of these equations can be solved easily by just checking the coefficients of the equation. And again, the idea is you can just go back to the original Rado by taking a power. Notice that here it's really important to have a fraction as an exponent. So square root of x is okay. X squared is not okay. Actually, one of the main open problems in the area, and we'll come back to this later, is if the Pythagorean equation x squared plus y squared equals z squared is partition regular or not. We don't know. This is extremely simple to state, but this is an open problem. This is open since the 70s. Now, other important nonlinear results, Bergelson, Fuster, and McCutcheon in 1991, if I remember correctly, proved that actually if you take a polynomial with no integer, no constant coefficient, then the equation x minus y equal p of z is partition regular. This is a strengthening of Sarkozy-Fustenberg theorem that I showed before. This is really new, and it's one of the most important results that we have so far about the partition regularity of nonlinear equation, because it covers a lot of cases and it has a lot of applications. Now, the idea is that here this is partition regular basically because of on the left-hand side of this equation I have x minus y. I'm a bit in a Rado situation. The sum of the coefficients on the left-hand side is 0. A question posed by and solved by Xivari, Martin, and Sarkozy was, what if I have a sum on the left-hand side? And actually, they managed to prove that even in the very simple case of x plus y equals z squared, you don't have partition regularity. And now, a simple question that they posed in around 2010 was, okay, what about this equation? This equation is interesting because x plus y equal to z is asking the partition regularity of an equation where you have a sum equal to a product. And in 2010, Bergelson solved this problem, and actually the proof was using ultrafilters and is surprisingly simple. So simple that at the same time, Hyman actually proved a much more general version of this result. He proved that all the Diophantine equations of the form a sum of variables equal to a product of other variables are partition regular. So it doesn't matter that you have a sum of two variables equal to a product of two. As many variables as you wish. And the idea was, again, to use the algebra of the ultrafilter, in particular the existence of a special ultrafilter that is, for those of you that knows what this means, this ultrafilter is both additively and multiplicatively IP. Now, in my PhD thesis, one of the main results that I proved is that actually also Hyman theorem is a particular case of a much more general phenomenon, because what is true is that you can construct a huge class of nonlinear equations that are partition regular just by starting from a linear one, and there you have Rado theorem that tells you when the equation is partition regular or not, and then you multiply every monomial by new variables. So this is what's written in mathematical form in this theorem. And the idea here was to the same kind of ultrafilters as Hyman, but here is where no standard analysis comes into the picture. So example, with this theorem, you can prove that equations like x1, y1, y2 plus x2, y1 minus x3, y2, y3 is equal to 0 is partition regular. Basically, you start from sure equation and then x1 plus x2 minus x3 equal to 0, and you multiply monomials by new stuff. Finally, the last results that I want to mention, new result that I want to mention, Di Nastro and Riggio proved that equations of the form similar to Fermat, where you have x to the n plus y to the n equals z to the k, are almost never partition regular. They are never partition regular if k is not one of m and n. And again, their proof was using completely non-standard analysis. And finally, Moreira, in a paper from 2018 or 19, where he actually solved a very important open problem here, partially solved a very important open problem in the area regarding the certain nonlinear configurations, he also proved that equations of the form sum of ci squared equal to y is partition regular whenever the sum of the coefficients on the left-hand side is 0. And this proof is, again, ergodic theory, a very smart use of ergodic theories. Or if you don't want to use ergodic theory, there is also proof that just use some properties of piecewise synthetic sets. These are not the latest results that have been published in the area. There are newer results that are a bit less nice to write down, but this was just to give an idea that you see that in the past few years, all these past 4 results are from 2015 onwards, is extremely active. Now, why ultrafilters? Ultrafilters came into picture actually not to study nonlinear equations, but because of Hyman theorem. Hyman is the same Hyman that I mentioned a few minutes ago. In the 70s, Hyman proved actually one of the most important theorems in combinatorics. He proved that whenever you split the natural numbers in a finite amount of pieces, in one of the pieces, you will actually find an infinite set X such that all the sums that you can construct starting from X are monochromatic. Sure theorem is Hyman where the set X contains only 2 elements, X1 and X2. Sure tells you that X1, X2, and the sum X1 plus X2 is monochromatic. Hyman managed to prove that actually you can take an infinite set X1, X2, X3, X4, and so on, so that all these objects are of the same color and all their sums are of the same color. Now, the original proof of Hyman is combinatorial. I tried to read it and it's a nightmare. Hyman himself stated that anyone with a very masochistic bent is invited to wade through the original combinatorial proof. It's really extremely hard to read, it's extremely long. Luckily enough, a few years later, Galvin and Glaser provided an almost trivial proof by using idempotent ultrafilters. So by using ultrafilters, there is a proof of this theorem that can be written down in one slide. What are ultrafilters and why are they important? Now, of course, I will give a super quick introduction to ultrafilters. There is no time to develop the proper theorem, but let's give an idea. An ultrafilter is actually a family of subsets of the natural numbers, because here we are focusing on the natural numbers. That has 4 properties. It does not contain the empty set as an element. It is closed with respect to superset, and it is closed with respect to intersection. These three properties actually are saying that U is a filter. You can add a 4th one, which is maximality. Maximality is whenever you take a subset of the natural numbers, either the subset is into the filter or the complement has to be into the ultrafilter. If you have all 4 of them, you have an ultrafilter. Beta n denotes the set of all ultrafilters on n. Ultrafilters do exist thanks to Zorn's lemma. But what's important for the applications of ultrafilters to combinatorics is that actually the space of ultrafilters has some extremely nice topological properties. First of all, you can easily define a topology on the space of ultrafilter by letting as a basis of open or closed sets for any A subset on N, the set of ultrafilters that contain A as an element is an open set. You can also define an operation of sum and similarly an operation of product on beta n. It's written here. It's not important to grasp the definition here. What's important is that this operation extends the usual operation on the natural numbers, but it has very different properties. For example, it's not commutative, but it is right continuous with respect to the topology. And actually what happens is that beta n with this topology, this operation is a compact, so very nice, right topological semigroup. And this opens the study of ultrafilters to a huge theory, the theory of compact right topological semigroups, that it has been developed independently and it has a lot of applications already. For example, a trivial one is that by Ali's theorem, any compact right topological semigroup contains an idempotent. So there will exist an idempotent ultrafilter. Idempotent meaning that U is equal to the sum of U with itself. If you take such an ultrafilter, you can prove Hyman theorem in one slide. And that was the original idea of Camping. Now, why ultrafilters that are family of subsets are important to study equations? Now, actually, there is a general theorem that holds much more in generality than the study of equations that is important here. It states the following: if you take a family of subsets of n, the following facts are equivalent. This family is partition regular, meaning that whenever you split the natural numbers in a finite amount of pieces, one set will belong to F, or F contains an ultrafilter. If you apply this theorem, given a polynomial P, to the family of those sets that contains a solution of the equation P equal to 0, you actually get that the following characterization of the Diophantine partition regular equation. A Diophantine equation is partition regular if and only if there exists an ultrafilter U, such that for every set A in U, you will find a solution to the equation called P, A1 AN equal to 0. And in this case, we say that U is a witness of the partition regularity of the equation. So, partition regularity of equations is actually an ultrafilter problem. You need to find special ultrafilters whenever you want to solve the partition regularity of an equation. And here is where non-standard analysis come into picture, because actually the non-standard methods are based on the idea of taking ultrafilters, which are complicated objects because they are family of subsets, and studying them from the perspective of numbers. So try to simplify the operations between ultrafilters and the properties of ultrafilters. What is non-standard analysis? Again, in 5 minutes, so a hyper quick introduction. So non-standard analysis, hyper methods, sometimes called, is based on just 2 properties, 2 ideas. The first is I have to study a certain set, for example, the natural numbers, and I have to study some property of this set. What can I do is I take the set and I enlarge it. I take a much larger copy of it, but I don't take a random larger copy of it. The larger copy is taken to have more objects inside there, so more methods to prove stuff. But actually, I want a weakly isomorphic copy. Weakly isomorphic copy means that I'm taking a larger copy, but I want to preserve as much properties as possible. So, for example, if you take X is the real numbers, when you do this kind of copy, weakly isomorphic copy, for those of you that knows the terminology, you're taking an elementary equivalent copy. What you have is that you have a larger ordered field, because being an ordered field is an elementary property of the set that contains the real, is larger, so it will contain also infinite elements, and therefore, since it is a field, infinitesimal elements, but R and star R cannot be distinguished by elementary properties. So you need to use non-elementary properties to distinguish them. But as far as elementary properties are involved, they are the same. By using a standard analysis, we are interested in the natural numbers. For example, you can prove that if you start from the integers, you do this standard copy, you will obtain a discretely ordered ring whose positive parts are the hypernatural numbers. The hypernatural numbers then will have the following structure. They will be, at the beginning, you have the natural numbers. But this is because, for example, the property of 1 being the smallest number of n is an elementary property. It's a very simple property of n. So the same has to be true for star n. 1 will be the smallest element of star n. So yeah, and the same for 2, 3, and so on. So you will have a copy of n, but then you go on. You have more points. You have all these other points, which are the so-called infinite hypernatural. And star n is the hyperextension of n, but what's important, again, is that you are constructing a larger object with the same elementary property. Addition can be extended, so star n can be made a semigroup, exactly as n is a semigroup. The same with multiplication, the linear order, so it's actually a linearly ordered semigroup, and so on. So basic properties remain the same. Not all the properties remain the same. Here is where a bit of experience with no-standard analysis is needed to grasp the structure going on. For example, the well ordering will not be preserved. The well ordering is saying that whenever I take a non-empty subset of the natural numbers, it has a minimum. This is not true for this no-standard copy, because, for example, the set of infinite elements cannot have a minimum. If it has a minimum, I take the minimum minus 1. This has to be finite, and if it's finite, it plus 1, it's finite as well. So this set does not have a minimum. So this is the basic idea about why such an idea is helpful. Well, there is plenty of different reasons. One is that actually using no-standard analysis, you can easily study infinite objects, because when you want to study infinite objects, you can use properly framed in no-standard setting methods coming from the study of finite objects. Analytic and measure theoretical methods have really simple formulations there. Moreover, if you want to study density problems that are not studied here, but in general, you can translate them in problems in no-standard analysis, and there they become, you can use measure theory, which is much stronger than just density. This is what's important for us, that hypernatural numbers can play the role of ultrafilters, and this is the whole idea behind this application of no-standard methods to ultrafilters. And no-standard proofs can be easily extended to more general settings. So if you want to extend some result that talks about natural numbers to a minimal groups, usually the no-standard proof will remain pretty much the same. Finally, since you're working in mathematical logic, you have also methods of mathematical logic, like enlargement, saturation, and so on. Now, what's these no-standard methods applied to ultrafilter look like? So really, what's the connection between the two? The idea is the following. If you are in the no-standard setting, you can say that two hypernatural numbers are equivalent if you cannot distinguish them by standard properties. Equivalently, if whenever you take a subset of the natural numbers, you do the extension. So for example, you take the even numbers, you take the extension, which is the set of those numbers in star n that are divisible by 2. Two hypernatural numbers are equivalent if they are both odd or both even. You do this for all possible subsets of n, you get the notion of U equivalency. And this is important because actually it's what identifies ultrafilters and hypernaturals. If you take an hypernatural number, you can associate to it an ultrafilter by taking the family of those subsets of n such that alpha belongs to the extension of the set. On the other way around, if you have an ultrafilter, you can associate to it a set of those generator of ultrafilters. So the set of those hypernatural numbers, so that the ultrafilter is equal to U alpha. And this is useful when we study a partition regulative equation, because actually now this problem can be framed directly in no-standard terms. An equation is partition regular if and only if it has a solution in star n, all made by U equivalent hypernatural numbers. What's helpful here is that you go from ultrafilters U to numbers in a no-standard setting, but it's like working with natural numbers. If we want to do this properly, we also have to find a standard characterization of sum and product. This is a bit technical. I will not enter into details here, but what you need to do is to consider iterative extension. So n extended to star n, extended to star n, and so on, so that you can apply the star also to the hypernatural numbers. And the properties that you need are really simple, because what you need is that if alpha is an hypernatural number, alpha and star alpha will generate the same ultrafilter. So alpha, this star behaves well with respect to generating ultrafilters. And the second is, in this setting, we can find a standard characterization of the sum of ultrafilters. The sum of U alpha and U beta is generated by alpha plus star beta. Notice a star is there because this operation is not commutative. And as I say, the translation in standard terms is that an ultrafilter is a witness of a certain equation if and only if you will find generators of the ultrafilter that witness that solve the equation. example, and this is the complete proof of Schur theorem using a standard analysis. So you see, of course, I cannot give a full idea here, but here you see why no standard analysis help. The proofs are really simple. If you start from Schur equation x plus y minus z, and you pick an idempotent ultrafilter U, then automatically take any generator of U, alpha. Then by everything I showed you here, star alpha generates the same ultrafilter because star preserves generating an ultrafilter, and alpha plus star alpha will generate U plus U, but U plus U is U. So you have alpha, star alpha, and alpha plus star alpha that all generate the same ultrafilter, and you apply the theorem above. If X is alpha, Y star alpha, and Z is alpha plus star alpha, you have a solution, all made by ultrafilter, by generators of the same ultrafilter. You have the partition regularity. The same can be applied, to nonlinear equations like X plus Y minus ZW. Here, just for you, if you want to read it, is the complete proof of this nonlinear equation. And since I have slightly more than 5 minutes left, I will skip these 2 slides. I prefer to spend a few more minutes talking about open problems, because these are what's interesting in the research nowadays. This is just a selection of problems. There is plenty more interesting problems out there. But one problem that I think is extremely interesting, and actually the one that I would really like to see solved in the next few years, is the Pythagorean equation, x squared plus y squared equals z squared partition regular or not? This is not known. Actually, a lot of related results are known. For example, in 2019, Heule, Kuhlmann, and Marek have proven that this equation is partition regular if we consider only 2 colorates. So if we take the natural numbers and we split them in 2 pieces, then in one of the pieces we will find a solution. What is not known is what if I split the natural numbers in 3 pieces? No idea. Actually, the problem is that their proof is computer assisted, and if I remember correctly, it's the longest proof ever found, because it's a lot of gigabytes of checking, because they checked all possible configurations in longer and longer initial intervals of the natural numbers up until a moment where they found, okay, for this number, all possible partition works. For 2 partitions, this is extremely hard to do with the computers, but they managed. I think they had the program running for 3 months, something like that. I talked with Kuhlmann, and he said that if they try to use the same method for partitions with 3 colorings, they would have to expect a few centuries with the same program running. So new methods are needed. Another thing that has been proven by Cho, Lindquist, and Prenville is that actually all the equations of the form sum of Ci xi to the k fixed, so like the Pythagorean equation, but as many terms as you want, and k can be 3, 4, and so on. These equations are partition regular if and only if you have a Rado condition, but provided that S is large enough with respect to k. This has to be expected because x cubed plus y cubed equals z cubed doesn't even have solutions. So if k is large with respect to S, you have this kind of Rado theorem. The problem is that when k is 2, for this theorem to hold, has to be at least 5. So for homogeneous equation of degree 2 with at least 5 variables, we have this result. But the Pythagorean has only 3 variables. So we don't know if this is partition regular or not. The second open problem that I want to mention is that for linear equation, there is a complete equivalence between the partition regularity on N, the partition regularity on Z, and the partition regularity of Q. The same is true for homogeneous equations. The problem is that if we go to non-homogeneous nonlinear equation, this equivalence is broken. There are equations that are partition regular on Z, which are not partition regular on N. The relationship between N and Z is anyhow quite clear. The real problem is what's the relationship between the partition regularity on N and Q for nonlinear equation. There could be no relationship at all, but I would be surprised. I think there is a relationship going on. It's just not clear which what it is. Another problem. Simple example of nonlinear equation where we have a very strong conjecture but no proof yet is that equation of the form linear piece equal to nonlinear piece homogeneous of degree 2, sum ci xi equals sum dj yj squared, is partition regular if and only if at least one of the two pieces, the linear part or the quadratic part, satisfy Rado condition. I'm almost sure that this is a theorem, so that this is true, but there is no proof yet, no complete proof. We know the proof in a lot of particular cases, not a complete proof. And this is a very simple nonlinear problem, so this will be interesting to solve. Now, in this talk, I talk about natural numbers, but all these problems can be framed also on finite fields. And on finite fields, there are more things known that for the natural numbers, but still there is not a complete characterization of which the Offentin equation are partition regular. So is it possible to find this characterization for finite fields? This is a slightly simpler problem than working directly with the natural numbers. So maybe we can find a characterization there and then try to use it to work with the natural number. Here I talked about finite problems, linear equations. Actually, a very interesting area with a lot of interesting open problems is what about infinite systems of equations? Hyman theorem talks about infinite systems of equations. Now, the problem is there we don't have a complete characterization even about linear systems. We don't know which linear systems of the Offentin equations are partition regular. We know a lot of examples of partition regular systems, a lot of examples of non-partition regular systems, but we don't have a complete characterization. Can U equivalence, so non-standard methods, be used here? Now, I think I have an argument that shows that actually no simple non-standard methods will work, but maybe a more complicated non-standard methods can be used. I don't know. Finally, this is the last open problem that I want to mention. So when you have partition regularity of an equation, it means that for any possible finite partition of the natural numbers, you have the partition regularity. Okay. When you don't have the partition regularity, it means that there is at least one partition where you don't have solution in any piece of the partition. Now, an important problem in Ramsey theory is usually to find the simplest partition, so using the smallest amount of colors to find a non-solution of the equation. This is an extremely hard problem, and usually it's studied directly by combinatorial methods, actually finitistic combinatorial methods. The idea is there maybe some ultrafiltered non-standard method that can be introduced to try to study this problem? Now, again, the feeling is no, because ultrafilters are not very well suited to study these finitistic problems. But again, I don't know, maybe yes, but there is the need for some smart student to find an idea to show us how to work there. Now with this, I thank you. Here is my email if you want to ask a question, and that's it.
Thank you, Professor Baglini, for your nice presentation. This presentation basically on pure mathematics. The students of Midnapore City College, I hope those are associated with this Google platform, they will enrich by listening to the lecture of Professor Baglini. May I request to the participants, if you have any questions, please share the questions with Professor Baglini. Any questions from the audience? I can take maximum one question from your end. No, I think there is no question at all. I must thank to Professor Baglini for your nice lecture.
Thank you.
To enrich the participants. Hope in future we will again get the opportunity to listen to your nice lecture.
Hello.
Thank you very much. Yeah. Yes.
Yeah, am I audible?
Yes, audible, please.
Yes.
Yeah, so I would like to ask a question. So if it is not too late. Is it
Yeah,
okay?
no problem. Yes.
Yeah, so you did describe a construction. I'm not much familiar with non-standard analysis, but you did describe that for integer. For example, for integer, there exists some z star or something that you are constructing, and z is weakly isomorphic to z star. So my question is, I need your opinion. So is that construction possible, like purely function in terms of function space? Like what I mean is, if you consider L infinity, little L infinity z, that is a function space. So in terms of purely function, so is there any possibility to construct another function space so that we can embed or we make a weak isomorphism between L infinity z and that space? So my motivation or my intention is that is there any possibility to study non-standard ergodic theory? Because if I can go to function space, and in that sense, or with that motivation,
Yes,
is there any
not
hope?
only it's possible, but it has been done actually, because these non-standard methods here show just for the application to set of numbers, but they are totally general. You can use them for any space that you have. You have a space of functions, you can do the non-standard version of that. You have a manifold, you can do the non-standard version of that. And so on. And actually for LP spaces in general, there is a lot of applications that have been done using non-standard analysis. For example, just to say, distribution theory, if you use non-standard analysis to construct non-standard versions of L infinity spaces, L2 spaces actually, you can there define distributions as functions, no more as functions. They're really functions that are defined, and you can use the internal scalar product of your space to define association and so on. So if you are interested in that, and you send me an email, I can point you to a few general references where this is done, but there is an intensive literature.
Yeah, sure. That would be very much helpful. I'll surely send you a mail. Thank you for your, yeah.
Thanks for the question.
Thank you, Professor Baglini. Now
Yes,
I want
thank you
to
again.
say to the organizer.
Thanks, Dr. Baglini, for your scholarly presentation. Now we will move to the last session of our webinar. I would like to request again Professor Sankar Kumar Roy to chair the session of Dr. Sadia Samar Ali from Saudi Arabia.
Very good afternoon to Professor Ali from India to Saudi Arabia. Hello. Hello. Hello, Professor Ali. Please, Professor Ali.
Yeah.
Yeah.
Hello.
Okay. Before introduce your lecture, first I want to say about you few words. Please.
Hello.
Yeah.
Can you hear
Please.
me?
Yes, yes.
Yeah. Okay, very good. So like it's really my pleasure that I'm the part of this 2 days webinar, and I actually missed the presentations of the other dignitaries. So definitely you guys are going to upload the video, so I will look into it and try to learn some more things from the scientists from throughout the world. So actually for this presentation, for the today's presentation, I just decided to go for some of a very simple thing, and those simple things can be applicable for the early researchers, I mean the early years researchers, because I also tried to learn it, and I felt like it's a thing which is very easily to be applied, which is easily to be well connected with the research fraternity. So based on that, I would be presenting one of my work. So that's already a published one, and further to that, we will see like what best possibilities are.
Yeah, Professor Ali, please wait. First, I want to give a little bit introduction about you.
Okay.
Am I audible to you?
Yes, doctor.
Okay.
Yes, Dr. Shankar, please
First of
go
all,
ahead.
first of all, I would like to thank Professor Ali. She is my close collaborator, and recently we published a paper also in very good journal. So, Professor Ali completed her doctors and masters from Aligarh Muslim University, India, and now she is holding the post associate professor in the King Abdul-Aziz University, Jeddah, Saudi Arabia. She has published more than 70 papers in different international journals of REFUT, like ISI, SCI, SSCI, Scopus, and many others. She is associated many organizations like Eurostream Organizer, iForce Organizer, and so many things. Basically, Professor Ali has a interest on research on sustainable practice in supply chain management and technology and innovation related to developing countries by using optimization and quantitative analysis, subcomputing, stochastic methods, and reliability methods. In a nutshell, Professor Ali has a broad spectrum on research. Now, I request to Professor Ali, please share your knowledge to cater the knowledge among the participants of Midnapore City College. Now your time, please, Professor Ali.
Okay, so before we start, I just want to check whether I'm audible to all of you. If we can do some testing part. Hello.
I think it is no problem.
Okay. Yeah, because if there is some problem, then I can connect with my headphone.
Yes.
That's also the possibility. Yeah. So that's why I'm just looking forward to. Yeah. Just give me a second.
Yes,
Yeah.
no problem.
Hello? Yeah.
Yes.
Is it better?
It is now. Okay. It is clearly audible, no problem.
Yes. So let's go ahead and let's rock it. Okay. So can you see my screen?
Yes, it is visible also clearly. You can
Very
make it
good.
larger a little bit.
Yes, I did. So I think now you can see everything and everything looks fine.
Yes.
Yeah, so this is one of the work where actually we try to have some based of the hybrid based model evaluation, and for that hybrid based model evaluation there are different techniques which are being used. And before I start something to discuss here, actually this is one of the area which I started researching, and that area was initially used to known as the green practices, and now if you see, this has been emerged as the sustainable practices, right? So in the sustainable practices, this is one of the components, like the green part, the environment part. But since there are the concepts which have come from the social impacts also, the economic impact also. So once we are going to combine all of these envelopes together, which is the social, environmental, and the economic practices, then the things are known as the sustainability. And I think in the today's era, everybody is conscious about to do something for the environment, do something for the social sustainability. And during the COVID also, we learned so many things related to the social impact, social sustainability. So my research is focuses on, started with the green, and then I took the step ahead. And once I took the step ahead, so definitely it is merging for the sustainable society, and it is merging for the sustainable manufacturing. So this is the thing I captured in my talk. And we took it some of the methods, which is the recent one. The one method, actually we started with the easiest one, which is a PLS-SAM method, which is a partial least square method. And this partial least square method, structural equation modeling is done based on that. And after that, the machine learning algorithms are used, and those machine learning algorithms are used to check the validation, to do the model testing, again the model testing, so that we can check, yes, the robustness is there. And then we use the IRT theory also, just to have the again the measurement predictions. So let's as I already told you, the motivation is nothing but it's actually falls from the sustainability practices. There are various goals which the UNDP has targeted. So one of the goal is the sustainable manufacturing. So looking at that, the sustainable manufacturing is being captured over here. And for any of the, actually, whenever we go for any of the model-based testing, or let's say the deductive testing, so there we try to check what kind of the model we can build up, what kind of the possibilities of the empirical analysis will be there. And once those empirical analyses are there, so we have to apply some hypothesis testing. So in our cases, we took the instances from 3 different theories. The first one is actually the institutional theories, and for the institutional theory, actually these are the outcome we kept in the mind. And once we kept these outcomes in the mind, so definitely the institutional theory is going to give us the benefits, because it actually deals with the external norms, and those external norms are the regulations, sanitations, what values are the the other stakeholders are there. I mean, the stakeholder which with whom we are going to deal with. And then internal factors are also there. Any organization, they do have the marketing, corporate communication, strategies, and policies. So we picked this instance and we integrated into our hypothesis building model. And then there is a resource base, because again the resource base, since it is talking about the sustainability, so that's why the resource based view are mostly taken by the researcher. We have taken the instance, we have taken the component of the resource based view, and we integrated, because our outcome is nothing but we would like to have the outcome, and that outcome was organization, resources, and the capabilities, and that we want to exemplify. And once we want to do that, so definitely this is the best another fitted theory which we have found will be best for our work. And then stakeholder theory. And for the stakeholder theory, we want to have, like, if supposing the government has suggested something to the organization, so how the organizations are taking those things, and and the regulations are there which is going to support the organizations. So once we are capturing all of these things, so it is actually positive relationship with all the stakeholders. So looking at that, three theories have been picked up, and then we decided how we are going to do the model analysis. And for the model analysis, we have to create the items, because items are nothing but, like in mathematics and statistics, we have the variables. So similarly here also, if we have the variable, so that particular variable will be based on certain concepts. So for that, we picked the items, or let's say the variables, from the literature. And once we picked those items, so those came around 72. And once we have found these 72 which are going to fill our requirements, then we decided to do certain kind of the validation. And for that validation, first thing first, we considered the industry experts, because the industry experts are the best fit, who can suggest, yes, this particular item will actually measure the green practices, or the sustainable manufacturing, or the sustainable society part. Looking at that, they have given us the suggestions, and some of the items we actually drop, some of the variable actually we drop from our findings. And further to that, we have actually done some items where kind of the overlap, I mean giving the same significance or giving the same meaning. Then we have done the rewording part, and based on the rewording part we dropped again few items because those were the duplicates, because in the duplicates item what happens, the problem arises further. So once we have done all of these reworking part, revision part, dropping the item, reconsolidations, then we just found 39 items which can solve our problem. And what is the meaning of the problem? That means we need to create the questionnaire, because without the questionnaire we cannot collect the data. So the questionnaire preparation is done, and after the questionnaire preparation with the 39 items has been done, then the questionnaire was actually distributed to various organizations. So, and those organizations were we collected the data from India. So those organizations we selected with a very keen interest, because not all the organizations are really keen for these things, because some of the organizations are in early stages of the green practices or the sustainable practices, etc., etc. So that's why it was little, it was not a little effort, it was kind of a effort which had took somewhere around a month and days. So then we got the connect from some of the presidents. There are actually, if you go to any of the setups, any of the built up of those organizations, then they have actually some of the association, and these associations are headed by some of the presidents. So we got connected with those presidents, and then we tried to collect the information, what kind of the practices, what kind of the things. And he was really helpful, the concern and the president, he was really helpful, and he connected us with the right organizations. So we have got the data collection based on so many factors, and if we see the so many factors, so definitely we checked their sustainability goals, and we checked whether they have integrated the green practices or not, and then we had checked the kind of the operations also, because if it is a new organization, then it's really difficult to ask them about the things, and then we have checked their certifications also, and based on that we decided, yes, these are the organization we want to collect the data. Then if as I have already told you, 39 items were there, but those 39 items have been segregated into various envelopes. And what are those envelopes? The first envelope was representing the sustainable green practices, but for the sustainable green practices, again we bifurcated the construct. Again we bifurcated the items into certain scales, and those scales was related with the green practices. Then there were the sustainable manufacturing related item, and how many items out of the 39 we picked? That was six items, and same was the case for the low carbon performance, and for the sustainable manufacturing we just found only 5 items are the variable which can be used for the measurement. So here comes the whole collection of the items, and that whole collection of the item, from the sustainable green practices, we had an item which was related to the green procurement practices. The another one was the green logistics practices, then the green product design and the processes, and the regulatory framework. So these are the main which was giving us a hint related to the green sustainable green practices. And after that the LCP was there, and these are so I'll just talk about in short, like how many organizations we targeted, what approach we used. So there were 900 organizations which we targeted in both the sectors. I mean, the sectors we took it from the north and the west, and the problem was, what was the problem actually? It was so difficult to collect the data. And once we have collected all the data, so out of 900 we just found that 300 valid responses, and those 300 valid responses was based on so many things. And what was those so many things? It was the category, what kind of the nature of the businesses they have, the year of the operation, the type and operations, the type and the operations, and what kind of the processes they are following, then what kind of the practices they have integrated, and how many practices they have integrated, and their environmental certifications and all. So we see here like 380 were received as a final, because some questionnaire were the half failed, some questionnaire we used to really do the multiple calls, and after having so many follow-ups by using that Dillman's approach, we actually got the 380 responses which we found suitable for the further analysis. And this was actually the model built up based on the theories. And here is the model. Yeah, we see here, this is green practices. This is all green practices. And for this all green practices, so for this all green practices, here is the green practices. So this green practices is going to improve, are going to give some kind of the low carbon performance, because that is the ultimate objective. And for that ultimate objective, these practices are there. And once the low carbon performance are achieved by these organizations, definitely it is going to help the society, and that society will be the sustainable society, and it will going to help the sustainable manufacturing. So this was the model built up, and for that we have found several hypotheses, because the empirical evidences with the help of the deductive approach is required. So here we are finding the green practices are having a significant impact on the low carbon. Same is the case for the other hypothesis also. The green logistics will have the significant impact on LCP. The green product design and the regulatory framework would also have the better impact or the significant impact on the low carbon performance. Now, low carbon performance will have the impact on the sustainable society. Low carbon performance will also have the impact on the sustainable manufacturing, and sustainable manufacturing will have the performances are the significant impact on the sustainable society. So this was the model which was created, and for this model, these were the hypotheses which we proposed. So there were 6 hypotheses which we want to test, so that further implications can be done based on the empirical evidence. And once we have the model building part, then the next comes is the measurement model. And what is that measurement model? In the cases of the measurement model, we have to actually check, we need to verify, and because if the verification is done, then we can go for the structural model. So for the measurement model, there is a requirement of the internal consistency, and that internal consistency is actually done with the help of the Cronbach alpha and the composite reliability part. There are certain benchmark value, and those benchmark values have to be checked, so that we can check, yes, the internal consistency is there. And the construct validity is actually related with the loading and the cross loading part. And it's so common because these days everybody is doing the factor analysis, and there all of these things are actually used. And then there is a cases of the convergent validity, and those convergent validities are also measured, because these are going to give us kind of the discriminate validity. Whatever we are trying to measure with the help of the specific construct, if the specific construct is sustainable manufacturing, so it has to be sustainable manufacturing. So whether this thing is true or not, that can be evaluated, that can be checked with the help of the convergent validity and the discriminate validity. And these are actually the several criterions. These have to be checked, which is Forner-Lercher criteria and HTMT criterion. So we have done the analysis, and just to check the measurement model accuracy. And in that case of the measurement model accuracy, these are the loadings, and these are the things actually which we needed. Loading we needed, and we needed this, so all of these things are done. So loading are here, then the average variance extracted values are here, Cronbach alpha is here, and this value is the value which is for the composite reliability. And for all of that, we have, this is actually for the reliability analysis. So for the reliability analysis, we have to check these two values, which is CR value and which is Cronbach alpha value. So what is the benchmark? Benchmark is like it has to be equal or more than a 0.7. So this criteria in our case got satisfied. So first criteria for the reliability analysis was okay for our case. Then we moved ahead with the convergent validity part. And for the convergent validity part, the AVE values has to be checked, which is the average variance extracted. And for the average variance extracted, these are the values. And these values are should fall in between these ranges, which is 0.5 to 0.7. So most of these are in between. There is some value which is actually little. Yeah. So this is related to the sustainable manufacturing. So we assume that it is like, as per the researcher, we found, yes, it can be applicable for the further analysis. So we also considered it and we moved ahead. After having the measurement, in the cases of the measurement model, reliability, convergent validity, next is the discriminate validity. Now for the discriminate validity, there are actually the values. This is actually the table which is for the correlation. Now, once we are checking the correlation, so we are going to check the correlation from the column side. And once we are checking the column side value, then we have to check this value, the value of the square root of the AVE. And that square root value of the AVE is actually here. This is the value, this is the value, this is the value. And in each and every column, this value has to be more. So diagonal values we will check, and this value has to be more in each and every column. So here, if you see, if we approximate, then the value will come near to this. So again, based on the instances, we assumed it is okay, and then we moved further. The discriminate validity is also considered applicable in our case. Then we are going to check the HTMT criterion, and this HTMT criterion says that the value has to be less than of 0.9, and all the value in our case except this value, except this value came satisfying the criteria. So values within the prescribed limit was found, and we can say that yes, all the constructs are actually distinct to each other. That means whatever the measurement we took it, supposing for the green logistics, if we took the 5 items, 5 variables, so definitely those 5 items are actually defining the green logistics. Same was the case for the others also. So all the constructs are distinct with each other. And then we try to check the multi-collinearity issues also for all of these constructs. And for that, we found that the values are all less than of 10, and less than of 10 values is actually applicable. And then all the testing part is done. So there is actually, whenever we do such kind of the analysis, which is known as the PLS same based analysis. So there is a very famous thing which is known as the CMB, the Herman's common method bias test. So it has to be checked. It is a rule, like some biasness is there in the response. Now to check the response biasness, this has to be checked. So single factor biasness test was conducted, and if the value will be more than of the 50%, so biasness exists. If it is less than, so the biasness is not there. So in our case, we found this value. So this value is actually satisfactory. So CMB, the common method bias also is significant, is okay in our case. So now we moved, once the measurement model is done, so we move to the structural model evaluation. And for the structural model evaluation, that is a kind of the path analysis. So here is the path analysis. So this is all done with the PLS SAM. So we see here like first, second, third, and the LCP is being measured, LCP as the construct. And these are the values of the R square, adjusted R square, in fact, adjusted R square. And those values are here, which is the adjusted R square values. So we are now doing the structural model evaluation, and for the structural model evaluation, all the values of the exogenous variables have to be checked. For the R square or for the blindfolding, we are not going to check the values for the independent, like in our term we say the independent variable and the dependent variable. So we are actually checking for the dependent one, and in this case, since we have found the construct and these are the latent variable, so those construct are actually our exogenous variables. So those are how many exogenous variables we have? 1, 2, and 3. So for all of this, we are going to do the checking for the adjusted R square. There is actually the F square values also. There is a values of the Q square also. So all those values we checked, and as per the classification, as per the recommendation, we found this value, we found this value. So all these are acceptable, and in fact this value is, which is 0.932. It is 10% higher as recommended by the Falk and Miller. Like Falk and Miller is the benchmark which everybody uses, and in this case the sustainable manufacturing is coming actually very, very low. The R square value is actually very low. So for the sustainable manufacturing, it is not actually, the sustainable manufacturing does not influence the low carbon and reflects that no contributions towards a sustainable society. So that's why if anybody is considering, for like our research, we considered sustainable manufacturing and the society. So there is a very less impact of that. That means actually that means that for the low carbon, there has to be some rigor, there has to be some more measurements, there has to be some benefits out of the carbon credits and all. So this was the structural model, which was evaluated with the help of the SAM PLS, and this was the model building we have done. And if you see, these are actually the loads. And the T, actually we have not shown the T value, because whenever we are checking the hypothesis testing, so there are two benchmarks which we can check. Either we can check with the T values, or either we can check with the P values. And for the T values, the recommendation is we have to compare with 1.96, and for the P value we are checking with the benchmark of 5%. And once we have done the checking, so all the values are actually found significant and the hypotheses are accepted. All these hypotheses are accepted. So if you see, green procurement has a significant impact on the low carbon, so this one is accepted. Similarly, all of these are accepted over here. The sustainable manufacturing has a impact on the sustainable society, so this was actually accepted here. Yeah, though we know that there is a very less impact. It's a very, I mean, that the value was, the adjusted R square value was very low, but then also it's been accepted. Then we have done the machine learning based classification testing, and for this we used support vector machine, decision tree, and the artificial neural networks. And this we done with the R for machine ML classifier, and we can see here, like for the SVM, for the ANN, for the GT, the values we have got it for all the endogenous variable. For the LCP, which is based on these practices, for the LCP based on the SS rating, and for the LCP which is based on the SM rating. So based on the results of the machine learning, SVM and ANN, SVM and ANN actually shows the better accuracy, and overall accuracy is actually better in the cases of the ANN. And SVM predicts, yeah, we can check here, like the SVM predicts the LCP, and how much is the accuracy for that? That accuracy is 92.63%. And ANN measures the LCP impact on SS. Yes, we can see that it's 98.24%, and here the accuracy is 92.10%. So these are the accuracy. And after the accuracy, we check the precision also. And for all the precision, all is good, because all of this is actually falling in the class of average to excellent, except one. This is also falling from average to excellent. Except the last one, which is for the sustainable manufacturing, the LCP based sustainable manufacturing rating. This is actually falling from poor to good. So all of these are okay. The scores are okay. Only the improvement which we are looking at for the prediction for the LCP and the SM, because that is going to that actually produce the results, and that result falls in between poor to excellence. And so for the we skipped ANN based algorithm, because that's the poor class predictor. Yeah. And then we have done the post-hoc analysis. And for the post-hoc, why we have done the post-hoc analysis? Because the items related to the LCP and regulatory framework was not widely spread in the research literature. So for that, we have done post-hoc analysis with the help of the IRT approach, item response theory approach. And once we have done it, then we have found that we see here, there are the items, those items actually whenever we do such testing, so we have to find the value of the alpha, and that alpha value has to be more than 1. But then we have to check the loads also, and once we check the load, so we found that in the cases of the RF5, which is the 5th item which falls for the regulatory framework, and LCP2, the 2nd item for defining the low carbon performance, doesn't load here. It doesn't have any value. Similarly here also, the LCP7, the 7th item, which is describing the construct of the low carbon, also doesn't load any value. So that means, what are those items? What are those items? Actually, those items are the items which has to be retested, or which has to be, because these items doesn't load. So as per the literature, we have found it, we wanted to check it, but then we have found that these items are not significant. And once these items are not significant, so definitely these are the organization who have given their responses to us. So those organizations are having a very moderate preferences towards those items. And those items are reductions of the carbon emissions, impact of the carbon footprints, and the water consumptions. That means these organization needs to focus on these things, and maybe in the future, once we are going back to them, they will get the better data, and as for the better data, this thing might be loaded. Yeah. So that was actually the presentation, and thank you so much. If there are any queries, so I am open for the discussion. But let me tell you how helpful this data collection was. So I just want some benefit which I got with the help of the data collection is, this is another publication which I did from the same sector data, from the same concept data. So this is, here we have used some other methodology. Here we have used the regression model, and after the regression model, again we have used the AI based technique just to validate the traditional perspective of the multiple regression. And this was the work which I presented today. So for the same data, we have done several work. And this is also the another one which is related to the low carbon performance, where same practices was there. We did some internal versus external practices based analysis. In what are the internal practices, what are the external practices, based on that what will be the better performances of the low carbon. So this was also from the same project and same data, and this is also from the same project and the same data. Here we have done actually the correlation based analysis, the colonial based correlation we did it, and for this we use the same green practices, but from that green practices we converted that into the further scale, and then we did the analysis. And so this is all actually we have done. Yeah, thank you so much. Yeah. Hello?
Ma'am, wait a bit, Esther is joining.
Okay.
Okay. Thank you, Professor Ali, for your nice motivational lecture on green practices. I am waiting to receive the questions from your end, from the participants of Midnapore City College. Any questions from the audience? No. Okay. I have a small question to Professor Ali. Could you please explain what do you mean by the sustainable society?
Sustainable society. Yeah, actually, in the cases of the sustainable society, we just want that, like if you can just consider the case of segregations of the garbage, right, at the houses, and then taking back that garbage according to the various categories. So this is nothing but one kind of the sustainability thing we are taking care of. In the cases of the sustainable society, all the reverse logistics part will be there. You want to buy a new car, so you will get the reverse logistics facility from the organization. They will come, they will pick the things, and then they will give you some economic benefits. So being a customer or the consumers or a citizen, we are going to get some benefits like this. Yeah.
Yeah. Thank
So
you.
it's
Thank
like
you.
we will be proud to pose ourselves as a eco-friendly consumers, right?
Of course,
An
of course.
eco-friendly
Yes.
Indian. Yeah.
Yes.
Because you know the fashionable terms are eco-village. Like these days, people go to see eco-village, right?
Yes.
So if you see our culture, so our culture was actually started and rooted in those eco-village. Yeah, but we lost the values in between. Now everybody is talking in these fancy terms, but these fancy terms we used to have.
Yes. Means sustainable goals. There are 17 goals are there, in which one of is sustainable society.
Yes.
Yeah.
Yeah.
Okay. Thank you. Thank you very much for your nice and motivational lecture. How to make
Thank you,
the
Professor.
environment clean.
Yeah.
I hope the participants will enriched by listening this your good lecture, and in future the young researchers, they can plan to motivate some doing research activities in these directions also. Thank you very much.
Thank you so much, Professor
Yeah.
Roy.
Yes. Now I request the organizer, please say something at the end of this lecture.
Thanks, Dr. Ali, for your very enlightening presentation. Now we have reached the end of the webinar. It has been enriching and invigorating 2 days for us. We have learned much from our eminent research persons. This enlightenment is what we hoped for. So I would like to request Dr. Saurabh Kantipatru, Assistant Professor of Mathematics, Department of Pure and Applied Science, to conclude the webinar with a vote of thanks.
So we have reached the end of our two-day international webinar. I thank Professor Sankar Kumar Roy, Department of Applied Mathematics with Oceanology and Computer Programming, Vidyasagar University, India. Professor Shyamal Kumar Mondal, Department of Applied Mathematics with Oceanology and Computer Programming, Vidyasagar University, India. Professor Alexander Vasin, Lomonosov, Moscow State University, Russia. Dr. Mohammad Akbari, Tootkaboni, Department of Mathematics, Pure Mathematics, University of Guilan, Iran. Dr. Sadia Samar Ali, Department of Industrial Engineering, King Abdul-Aziz University, Saudi Arabia, and Dr. Lorenzo Luperi Baglini, Department of Mathematics, University of Milan, Italy, for their insightful lectures and for giving their precious time to us. I thank Dr. Pradeep Ghosh, Director, Midnapore City College, for his valuable support, and Dr. Sudipto Chakraborty, Principal, Midnapore City College, for his constant advice. I would like to thank Mr. Abhishek Das, office in charge, for his positivity, and Mr. Suman Mullik, technical in charge, for his constant backup. At last, I thank Mr. Satyajit Bhuya, Dr. Somen Kumar Das, Mr. Abhishek Chakraborty, and Mr. Jagannath Samanto with Vishwajit Bhuya for their efforts in making the webinar success. Finally, I would like to thank all the participants. I wish we will be doing more webinars like this in future. Thank you all again.
Satyajit, hello Satyajit, please end the session.
Yes,
Please end the session.
yes, sir. Thank you all for participation. Thank you. This is we reach the end of the webinar. Thank you.